studying calculus today. We have gone, so we've broken the pattern, right? The pattern is generally we start by revising what we studied in the previous class. Why are we studying calculus? Anyone? Anyone else? So what is the topic of today's class? So in the previous class we were discussing Bayesian linear regression. What is the next natural step? Bayesian logistic regression. But why does it require us to understand or revise some amount of calculus? We already know all the calculus required, right? That's assumed. So Bayesian linear regression, we were trying to solve, we were trying to find out a posterior, and we said that we chose a normal prior. इसमें echo बहुत आ रहा है. Am I audible? थोड़ा और कम. Can you hear? थोड़ा और कम. Okay, can anyone still hear a hum? ठीक है. Okay. Okay. So we were trying to solve the problem for finding out the posterior in linear regression, in Bayesian linear regression, and that we said that we could find out efficiently because the prior was a normal distribution, the likelihood was a normal distribution, and the posterior turns out to be normal distribution as well. So because of the conjugacy of normal, we get another normal. Whereas for logistic regression, what is the prior that we typically choose? Logistic regression, not coin toss. So what kind of penalty do you put? What kind of penalty do you put in classification? What term do you add to classification loss to make it regularized in the previous semester's course, not this semester? L2 penalty, right? L2 penalty corresponds to what kind of a prior? Normal prior, right? So normal prior, and what is the likelihood for logistic regression? Bernoulli. So normal, Bernoulli. They don't give you a nice posterior which you can compute analytically, right? So therefore we'll need some approximation methods, and today we'll study the method known as Laplace approximation, but that requires us to know a certain term known as Hessian. I assume that most of you would know it, but I just wanted to again go through it quickly so that all of us are on the same page. Right? So we'll start off with a simple derivative. We say that this is the change of function with respect to the change in the input or the argument. So nothing fancy about this. If a function is 3x squared, the derivative is f dash x as 6x, which means that for every unit change in x, the value of fx changes by 6x. Right? That is the interpretation of f dash x. If we had to implement this in either JAX or Torch, the code is fairly straightforward. In JAX, we are defining a function fx, and we obtain a new function which is called, which you're able to call as jax.grad of f, which is the new function. So now this grad f will take the same parameters as the original function, and you can give in any value and you will get the derivative at that particular x. Right? So there is a slight amount of stylistic difference between the way JAX does and what typically Torch does. But Torch also now provides a new API where you can do something fairly similar. I just wanted to show the code that it is only 3-4 lines of code in order to get the derivatives. For Torch, we just write the function. The function is the same as before, but we define the x as a Torch tensor. We calculate y equal to f of x, and all this while the computation graph is getting constructed, going from left to right. When you call y dot backward, the gradients are filled up, the gradient values are being filled up, and that's where we can access the derivative equal to x dot grad. Right? So there's a slight difference in the way these two frameworks are giving you the gradients, the derivatives. Partial derivative, we all know the term. So this is the derivative with respect to a specific input. Let's say we have a function of two inputs, 2x squared plus 3y. We can find out the derivative with respect to x, which is the derivative of 2x square, which is 4x, and the derivative with respect to y, which is derivative of 3y, which is 3. So these two are the partial derivatives. If we were to again write these in Jax and torch, so in Jax we can write grad fx, grad fy. So the gradient of f with respect to the first argument and the gradient of f with respect to the second argument, we are indexing 0, so therefore 0 and 1. We could find it this way, or in torch we can again first write the entire forward path, which is z equal to f of x comma y, called z dot backward, which fills in the gradient information. At that point you can access the gradients. So it's a useful exercise to understand how these two different frameworks will operate and when do the gradients become available, right? So if you were to call x dot grad before z dot backward, what do you expect to see? None, nan, whatever is the default interpretation of when the gradient has not been computed, or an error perhaps. The gradient is a vector which is combining the partial derivative with respect to the different input variables of the function, right? So we have used the same function as before, 2x square plus 3y. I've just put the partial with respect to x and partial with respect to y. Right. So at this point we have not done anything new. We can also write a simple piece of code. Now you see that I have just made the code a little more efficient. So previously I had calculated the gradient with respect to, or the partial with respect to x and partial with respect to y separately. In this case for Jax I am directly computing the gradient with respect to the function f with respect to the two arguments 0 and 1, right. This will construct the vector automatically for you. In torch also I am doing the same thing, but I am, in this case this particular implementation of torch that I am doing is slightly inefficient, right. So I am computing x dot grad, y dot grad, and I am then putting them in a torch dot tensor object. Right. So I compute z dot backward, which gives me the gradient with respect to x and y, and then I manually construct the gradient tensor. Right. Could we do something better? Lesser lines of code. What might you do?
We can make the function f take
A tensor.
of two variables or a list of two variables.
Okay.
Then the gradient will be tossed just the list dot grad.
Okay, excellent. That's what I had in mind. You modify the function a little bit. You change this function to f2 vectorize, which takes in a certain amount of input. I'm using the input as an argument. It's a bad idea because input is a reserved keyword in Python. X and y, you break the input into x and y, you return the function, its value, and then I create a new input object, input tensor containing both x and y, and then I can directly get the input dot grad, which will give me two elements, 8 and 3. Right? This is more efficient, and you'll see this pattern in some libraries where they they just get in a single argument over here, and then they break it into different arguments over here. Has anyone used SciPy's optimization? Anyone else who's used SciPy's optimization? Okay, 2 people have. Let's just see if there is any similar thing there. I'm just looking for an example. Right. So it is using the Rosenbrock function. Right. It is giving you some initial values x naught. It is trying to find out the optima in this dimensional space. And the argument to this function is just a single argument, and then the objective it is constructing based on the specific indices. Right? This is similar to the argument unpacking that we had done here in the previous example. Here they are directly using the indexing to carry this out. Right? And this is the optima that they have obtained. Right? So I just wanted to show that this is a common pattern in various optimization libraries. where the input to the function is, which you are trying to minimize, or the objective is a single variable, and then you break it up into the different components. Just makes the design more efficient. So now we come on to something which we may not have studied a lot, Jacobian. Does anyone know what a Jacobian is? Okay. A very few set of people know what a Jacobian is. So I think the simplest way to understand is to just take this example. You have a function of 3 variables and the output is now a vector, right? All the previous cases that we've been seeing, the output was a scalar, right? We have vectored output and we have multiple inputs, right? We are trying to find the Jacobian of this function. So you find out the partial with respect to x for the entire vector, right? So x square plus y square, what is the partial with respect to x? 2x. Y minus z, what is the partial with respect to x? 0. X square plus y square partial with respect to y? 2y. Y minus z partial with respect to y gives you 1. X square plus y square partial with respect to z gives you 0. X square plus y minus z partial with respect to z gives you minus 1. Right? So that's how you have computed this Jacobian matrix. So it's multiple outputs. Right? Any questions in this? And we can again write this quite easily using torch. I'm using torch.autograd.functional.sf. This API might have changed in the previous few months because of the way Torch team has also been looking into FuncTorch project, which has fairly similar API to JAX. So this code may not work exactly on the latest version. We'll have to check that. So all I've done here is that I've created 2 functions, f1 and f2, which are corresponding to the 2 elements of the vector I'm trying to create. So x square plus y square, and my second one is y minus z. And okay, there is a bit of an error, the code is not indented, but essentially when you want to compute the Jacobian, all you do is you call f.Jacobian of the function and you send in the values with respect to which you want the Jacobian to be calculated at. And we found out that the analytical values was 2x, 2y 0 and 0 1 minus 1. If you put x equal to 2, you will get 2x as 4, put y equal to 1, you will get 2 here, and put z equal to 3 is anyway independent of z, and then 0 1 minus 1. So we are able to confirm that this is indeed the correct implementation of Jacobian here. The next topic is Hessian. How many of us have used or known about the Hessian? Okay, so a lot more people know about the Hessian. So where have you used the Hessian, or in what context do you know the Hessian? Okay, anyone else? In what context do you know or have used the Hessian? Okay, good. So multivariate Taylor series, Laplace approximation, both of these terms we are going to study today. Anyone else who has used the Hessian matrix? Okay, okay, all of you have used it in slightly similar context only. So the Hessian we can think of as the second order partial derivatives, but of a scalar function, right? So thus far everything that we have seen apart from Jacobian is scalar functions. The definition of a scalar function is that the output is a single number that you will obtain, right? They can have multiple inputs, but the output is a single scalar. So these are all scalar functions. Jacobian you had multiple outputs, so it was a vector function. For the Hessian also we will consider a scalar output only, so it's a scalar function. In this case it has 3 arguments, x square plus y square plus x y z. So we can compute this Hessian matrix as you find out, so you have the first term as del 2f by del x1 square. So you find out the second derivative of x square with respect to x, that turns out to be 2. You find out the derivative of f with respect to x1, x2. So with respect to x, y, z, if you're trying to find out with respect to x and y sequentially, you'll get just z, right? X, y, z with respect to x will give you y, z, and y, z with respect to y will give you z, right? And similarly, you will be able to obtain with respect to the other terms, right? So this is the construction. This is the general formula that you'll use. And the code is again fairly straightforward. You can define the function. Importantly, it's a scalar function, so a single function would suffice. I've created x, y, z values, and I'm calling f dot Hessian of the function f with respect to the different function arguments. And this is indeed the correct answer as verified by what we'd previously seen, right? Okay, so let's soak in this for a minute. The Jacobian is giving you, the partial derivatives of the vector valued function. The Hessian is giving you the second order partial derivatives of a scalar function. Right? Now, can you take 2 minutes and try and write Hessian in terms of Jacobian of something? The hint is that the Hessian is the second order derivative, partial derivatives, and the Jacobian is with respect to a vector valued function. Again, feel free to discuss with your partners, with your colleagues, neighbors. Jacobian. Any other answers? Okay, let's wait for 2 more minutes. Let's wait for 2 minutes. Another hint is to somehow use the gradient term. The gradient gives you a vector, and Jacobians can consider vector valued functions. So that is the hint. So to understand the relationship between Hessian and Jacobian's gradients, let's take the same example. So because we have to somehow compute the Hessian, which means that the function of interest has to be a scalar vector, scalar, right? So then we can take a function like this. We can first compute the gradient. The gradient of a scalar you can easily compute. We know that it will turn out to be a vector, right? Now, for vector valued functions, when we are trying to find out the gradients, what is that thing called? That is the Jacobian, right? So with respect to this vector valued function, we can compute the Jacobian, and it will turn out to be the same as the Hessian for the original function. Right? So then it's also interesting to see how the libraries would go on implementing this. Do they directly find out the Hessian? Do they have to pass through the intermediate stage of finding the gradient and the Jacobian then? So that is left as an exercise. I think this slide I would highly encourage you to, if you want, you can keep a printout just to ensure that you retain all the terms. Jacobian is vector valued function, and the output would be something like this. In this case, it's a matrix, right? Hessian is a scalar valued function. The output is again a matrix. Derivative is with respect to a single variable. The input is also single variable. The output is a scalar. Partial derivative, you can have multiple inputs. The output is a scalar of multiple inputs, and you can find out the partial with respect to each of the individual inputs. And the gradient is the whole vector that you get when you figure out the different partials, right? So only the Jacobian has a vectored output. All of the others have scalar outputs. And for the derivative, partial derivative gradients and Jacobians, we are considering the first order partial derivatives like things, whereas for the Hessian, we are considering the second order. Any questions in this? Okay. We'll go back and just breeze through what we studied in the previous class for the multivariate normal so that we get back the context for Bayesian logistic regression. We started off with the multivariate normal distribution. We looked at the PDF. We looked at the definition of what the covariance matrix means. We looked at a few examples of different covariance matrices. We looked at 3 specific types of covariance matrices. What kind of a covariance matrix is this one? Spherical, because you have the diagonals are the same. The other diagonal elements, non-main diagonal elements are all 0. We could have had something in the off diagonal elements as well. So in this case, it's a full covariance structure. But if in the previous one, instead of 1, 0, 0, 1, we had 1, 0, 0, 0.8, then that becomes a diagonal covariance matrix. Right. We then looked at Bayesian linear regression. We had already seen what the theta melee looks like. We had seen what the theta map looks like, assuming a prior. And we said that we wanted to get something like the following, where we have the uncertainty in the predictions, which is coming because of 2 sources. Which are the 2 sources of this uncertainty? The noise as a part of the observation, from the modeling itself, right? So the noise coming from the data or observation is known as aleatoric, and the noise coming and the uncertainty coming in from incomplete model, like not knowing everything about the model, is known as the epistemic uncertainty. And this was the important slide where we looked at the graphical model. We put a multivariate normal prior on theta. The way theta is linked to the output is through this function xi transpose theta, and our output yi is a normal distribution with the mean xi transpose theta and some noise sigma. And we said that if we choose this prior, which is multivariate normal m naught s naught, and the likelihood, which is again normal, we will obtain a posterior, which is again a normal distribution, multivariate normal distribution with a mean mn and the covariance Sn. And then we did this proof by looking at log joint, and we looked at the specific terms of theta. Some were quadratic in theta, some were linear in theta, and some were independent in theta. We collected those terms, and then we said that let's assume that we know that the output is normal of the posterior is normal in theta with parameters mn and Sn, and we expand this out. We obtain an expression containing terms which are linear in theta, quadratic in theta, and independent of theta. And then we match the terms to get this sophisticated looking expression in terms of Sn and Mn. We said that the important thing going ahead, the way we produce the graphs for prediction, was the posterior predictive distribution, which involves finding p for a new y given a new x and the previous data that we have seen. That involves integrating out theta. So introducing theta and integrating out theta, which again turns out to be normal distribution. This is again calculatable because of the special properties of the normal distributions. For all the distributions, we will not be able to even compute this integral, which will happen for Bayesian logistic regression, we will see. And we saw that there are 2 terms here. So our y star is distributed with a certain mean x transpose mn, right? So mn is the mode of the posterior. So it's theta, basically some term of theta, right? So x transpose theta term, which we already know, but the theta is the mode of the posterior. And then we have 2 terms causing the variance. The first one is what? X transpose Sn x. What term is that called? The model uncertainty or the epistemic uncertainty, and the second one is the aleatoric uncertainty or the noise. And then we looked at certain examples. Questions on this? Okay. So then we'd go on to Laplace approximation. So without having heard of this term before, Laplace approximation, what do you think it might mean? This question is only for those people who have not heard of this term earlier. Where have you heard the term Laplace? Okay. Laplace transform, okay. So there seems to be some scientist whose name is Laplace, right? And Laplace distribution also. We saw that in the initial lecture when we were going through some distributions. It is similar to the normal distribution, but it has a lot more mass near the near zero as opposed to the normal distribution. So what do you expect Laplace approximation to be? Approximating something with a Laplace distribution, right? It will turn out to be approximating something with a normal distribution, Gaussian distribution, not Laplace distribution. So the nomenclature, the naming is slightly off here. So it's also easier to understand Laplace approximation as normal / Gaussian approximation. So here the Laplace is not for the distribution, it's for the mathematician who created this bunch of theory. So there will be two topics which we need to understand in order to get a good understanding of Laplace approximation. The first one is some Taylor series expansions, which we have studied in a lot of previous courses, but we'll see again why we need that. So generally when we talk about Taylor series expansion, the credit is given to the scientist called Brooke Taylor, and this is the scientist called Pierre Simon Laplace, who developed a bunch of theory in probability theory, etc., and some distributions, right? So I didn't know much about this scientist Brooke Taylor, and I wanted to little bit understand the history. So I looked up the Wikipedia article for Taylor series, and I also looked up. That's where I figured out that there is this particular scientist called Brooke Taylor, right? So this is where Brooke Taylor is being mentioned, right? But interestingly, if you go through this history article in Wikipedia, it mentions something like in the 14th century, there was someone known as Madhav, not our TA, some other Madhav from Kerala. And it says that he found the Taylor series for trigonometric functions of sine, cosine and arctangent. Right? This is 14th century, and 1670 James Gregory and John Collins, several Maclaurin series. So Maclaurin is another scientist's name. Then Isaac Newton has also independently discovered these things. So it mentions Newton had a cumbersome method involving long division finding out these things. And interestingly, it says that Isaac Newton wrote down the explicit statement for Taylor and Maclaurin series in an unpublished book, but this work was never completed and the relevant sections were omitted. When he published this book, Quadratura, I can't speak that, Curvarum, and then in 1715, this was finally published under Brooke Taylor. Right, so this is some limited amount of documented history present on Wikipedia, which mentions that this idea has been around and a lot of people have independently discovered this. And if you go to Madhava's series, you will see that this is the expansion which has been given. Importantly, they mention using modern notation. So it seems that Madhav had some different way of representing the same thing. Right. So this is the notation that had been given by Madhav, slightly different than the current one. And then it also importantly says that the recent literature in this series is sometimes known as Madhav-Newton series, Madhav-Gregory series, Madhav-Leibniz series, etc. I had never heard of these terms. I had only heard of Newton series, Gregory series, Leibniz series, etc. But so this was a good article to just get a sense of the amount of work which had been done previously. And if you notice, the series looks identical to the way we currently use these series, polynomial expansions, which is exactly what Taylor series does. So that was a bit of history. Again, I'm relying totally on what Wikipedia says, which I think could also be, which may not be perfect. So here is an overall idea of why we are discussing Taylor series, Laplace approximation, these different terms. So I've been saying this repeatedly in the course that the posterior may be intractable. You may not be able to compute that integral. So P of theta given d is P of d given theta times P of theta divided by the denominator. The denominator is integral of p of d given theta and p of theta over all possible values of theta. And that for many cases, in fact for most cases, may end up not being computable. It turns out to be an intractable computation. The numerator is easily computable, right? The numerator is the joint, which is p of d given theta and times p of theta, which is what we've been optimizing thus far to get the map estimate. But the denominator is incomputable, is intractable, and we can say that even if we don't know the denominator, let's assume that it to be some z, right? So we can say that the posterior would be generally of this form, p of theta given d equal to 1 over z, p times d of d comma theta, which is the joint, right? So what we're saying is that because we don't know this z, right, and we still want to compute the posterior, right, can we then make a Taylor series expansion around the map estimate of what we'll see? So we say that p of theta given d, we would approximate it to be some normal distribution whose mean is the variable of concern is theta, whose mean is theta map, and whose covariance is given as the Hessian inverse of the negative log joint evaluated at theta map. Right, so it's a lot of terms. Let's go over them again. So the first term is easy to understand. It's a normal distribution whose mean slash mode is theta map. Right, so we're centering. We're saying that let's assume that that is the best estimate. That's where we'll have the most density. Right? Theta map naturally makes sense. And then we have to figure out the covariance term. Right? So first we just look at what f is. F is negative log joint. Right? So negative log joint we know how to evaluate. Right? That is just log, negative log joint is just negative log likelihood plus negative log prior. And we have been optimizing that in the assignment also to obtain the theta map. Right? So that we know we can obtain theta map using an optimization. You obtain the Hessian of that function, right? Evaluate it at theta map, right? And then you find out the inverse of that matrix. Why we do that, we'll see in a minute, in a few slides, but that's the overall theme, right? So then we go back to Taylor series. I am hoping each of us knows what this Taylor series expansion that I've written. So we are trying to approximate a function via some polynomial expansion, right? So it becomes very useful in various cases, and like in and 3 Blue 1 Brown has an excellent video on this. I think we showed that video in the previous run of the course also. So we are trying to make a approximation f tilde of x, which is evaluating the function at around a point x naught. So we say this is same as f of x naught plus the first derivatives. In this case, it's a 1D series. So then f dash x naught into x minus x naught plus so on and so forth. Right. So that's the general idea. Let's try and approximate this function f of x equal to sine of 1 plus x, right, at x naught equal to 0. So we can take the polynomial approximation, the polynomial degree 0 Taylor approximation of this, right, at x naught equal to 0. It gives us f tilde x equal to 0.84. Is this a good estimate? Why do you say so? So it's a good estimate at least for the point x naught. It is the exact value at x naught because that's what the definition is. So at x equal to x naught it is correct. At all x is slightly away from x naught, it's not a very good estimate, but it's a very simple function form that you're using. Okay. What do you expect to happen when we put in the first order polynomial degree? What will change? Currently our estimation is a line parallel to the x axis. What will happen if I choose Taylor approximation with polynomial degree 1? Sorry, can you be a little louder? It will be a slant line. Can you tell me what the equation might look like? Sorry? No, it's degree 1 at this point of time. This is degree 0. Degree 0 means just parallel to the x-axis. Degree 1 would be a line, but what might that line look like? Sorry? Tangent to at what point? X naught. Okay. So, but can you tell me the equation of the line without actually solving it? So, y equal to mx plus c, right? Can you tell me the c? F of x naught, right, which is already 0.84, right. So, you will see that as we will go on making the expression better by increasing the number of polynomial degrees, we will always be adding to the previous expression. So, in this case the previous expression is f tilde x equal to 0.84. When we make a first degree approximation, we do not get rid of that 0.84, right, it stays there. So, you can just easily keep adding terms. So, then the expression becomes 0.84 plus f dash of x evaluated at x equal to x naught times x minus x naught raised to power 1 by 1 factorial. So, it turns out to be plus 0.54, and now the approximation seems to be slightly better in the vicinity of 0, better than the previous one. Now, with degree 2 we get even better approximation. Degree 3 the approximation is slightly better. Degree 4 it is now also trying to make an approximation in this zone between -5 and 0 and between 2.5 and 5. And degree 5, degree 12 it looks like a fairly good expression at this point. Right. Okay, any questions on this? So, if we were to write some code on this, we can see this function f of x, which is sine of x plus 1, and for the order that I am trying to compute, there is a nice trick that we have leveraged here, f equal to grad of f. Do you see what is happening here? So, in the previous iteration, so instead of computing, so we have to compute these f dash x, f double dash x, f triple dash x, so on and so forth. I just recursively keep calling f equal to grad of f, right. So, in each iteration I am computing a gradient over the previous function, right, and that is all we need to do. There is some additional bookkeeping that we need to do. We are also calculating the factorial of I. Right, this is just an interactive animation showing if you vary the degree, you can keep getting better approximation. And here you do not seem to gain anything if you go beyond 12, but let us go till 15 and see what happens. Sometimes the output does not refresh in VS Code for such interactive things. So, even though I have changed the arguments, I just wanted to check without that, did not work out.
No, on those 3 dots there is option to clear out, like on the cell.
Okay, so now we have till 12 we have already seen, right. So, there is only very minor changes which happen near the extremities, right. So, if we increase the range a little bit, we will see some improvement still. So, this was for 1D series. We have the same idea for n dimensional series, where now the functional has to be we have to be a little careful with how we evaluate this function or the approximation. We have now the inputs have changed to vectors, therefore, they are all written in bold letters. F tilde of x is f of x naught plus the gradient transpose, right, and multiplied by x minus x naught plus half of x minus x naught transpose times the Hessian evaluated at x naught times x minus x naught, and after that it is more complicated terms, higher order terms. So, another thing which is typically done in a lot of such approximations to make life simpler is to consider only certain degree terms, right? Only, let us say, first degree, second degree, third degree term. Right. So, here we will be only looking at the second degree term for today's class. And I would encourage you to again go back and see the relationship between Taylor's series and gradient descent in second order methods. So, with this now it should become clear what we are trying to do. We can, similar to the way we approximate 1D functions, we can approximate a 2D function. It is now a complicated sign of 1 plus x1 plus x2 function. We are trying to get an approximation around x naught equal to 0, 0. You can see the function is a very wiggly function. For the polynomial degree 1, we will get a 1D curve in this space, which would be a plane. Right? And if you want to understand that in an easier way, we look at a cross section at x1 equal to 0. Right? At x1 equal to 0, we can see that our approximation is now a line. Right? We can go for degree 2. Beyond degree 2, the calculations, the matrix methods, all of these start becoming slightly more complicated. So, therefore, I am in this class, I am just showing till polynomial degree 2, but the idea will still remain the same. You will start getting better fits as you increase the polynomial degree. And now we come on to the main topic for today, which is known as the Laplace approximation. Any questions till now? Okay. So, we are given this unnormalized density. So, for the lectures going forward, we will call this term as the unnormalized density, which is P of d given theta. The normalization constant is z. So, our posterior is the unnormalized density divided by the normalizing constant z. We can rewrite this as 1 over z e to the power minus f times theta, where f of theta is minus log p d comma theta. Right. What do you think the term f of theta is called? Log joint? Negative log joint? Right. F of theta is negative log joint, which is the same as negative log prior plus negative log likelihood. Right. So, f of theta turns out to be the function which we have been optimizing thus far to get the theta map, to get the map estimate. Right. So, all we have done is just rewrite P of theta given d in a slightly different way, where we have explicitly brought about the term which is our objective function f of theta, which is negative log joint. And at this point, we know that the mass would generally be concentrated around theta map, right, because that is the definition of map. It is maximizing your posterior there. Right. You would expect a lot of mass there, not necessarily always, because you can have things like multiple modes, etc., but you would still assume a lot of mass around the theta map estimate. So, what we are now trying to say is that can we approximate, can we get a Taylor series approximation around theta map of the function f of theta, right. F of theta has its mode as theta map, right. So, it is any function like the function which we had here, like f of x1, x2 is some function. Similarly, we will have f of theta 1 and theta 2 as some function. We are trying to get an approximation around that. We are trying to get approximation not around any point, but around the mode. Right. That mode is theta map. So, what we are saying is that let us approximate f of theta as some f tilde of theta around theta map, around theta equal to theta map, using the Taylor series expansion only up to second order terms. So, it becomes f of theta map plus the gradient of f evaluated at theta map transposed times theta minus theta map plus half of theta minus theta map transpose the gradient of f of theta map times theta minus theta map. Right. So, just soak in this expression And let me know if you can simplify this in any way. No, you already know this because you've done this in the summer. So typically drawing a picture would help. You assume some unimodal distribution, right? Make a very simple unimodal distribution, center it at theta map, right? And then see if this gets you some hint towards simplifying this expression a little bit. The hint is that it has got something to do with the definition of theta map, the way we define theta map. What exactly is that? Okay, let's see if there are more answers. Who will have figured out the answer? I have some answer. Okay, so another hint, one of the terms, we have got three terms, essentially got three terms. One of the term will become 0. Which one becomes 0? Okay, the first order term becomes 0. Why? There is nothing known as MLE in this expression. No, you said MLE. Theta map is the mode of what function? F. What is the function f here? Negative log joint. Theta map is the mode of that, or it's an optima of that. At an optima, the gradient becomes 0. Right? So that was the hint. This delta f term is the gradient. If you evaluate the gradient at the optima, it becomes 0. So therefore, the first order term goes away. Right? So we are left with only a constant and a second order term. Right? Does the second order term remind you of anything you have seen thus far? The general form of it, not the specifics of the things written over here. Multivariate normal? That is indeed the case. So we have written f tilde theta to be f theta map, which is a constant, plus the gradient of f evaluated at theta map transpose times theta minus theta map, which is the first order term, plus the second order term, which is half, which is a theta square like term. So it is half of theta minus theta map transpose the Hessian evaluated at theta map times theta minus theta map. Given that theta map is the minimum of f of theta, it's an optima, so the gradient becomes 0. Therefore, our expression is simplified to f tilde theta equal to this f theta map plus the second order term. And we know that the the second order term has this term called the Hessian evaluated at theta map. Right. Go back to where we started. P of theta given d equal to 1 over z e to the power minus f theta. Right. We have now got some approximation for f of theta. What is that? What is the approximation that we have? F tilde of theta. Right. Why don't you do this exercise? Just note down this particular slide. P of theta given d equal to 1 over z e to the power minus f theta in your notebooks. And once you have noted this down, you should see if you can substitute f of theta with the approximation f tilde of theta and get something interesting. So, in the previous expression that we had seen, just substitute f of theta with f of theta in this expression, P of theta given d equal to 1 over z e to the power minus f theta. Instead of f of theta, you write f tilde of theta, which contains a zeroth order term and a second order term. Okay, once you do this, what do you expect to get? It'll take a couple of minutes. Okay, good. So, we had this expression P of theta given d equal to 1 over z e to the power minus f theta, where f theta was a negative log joint. We can approximate this to be, so using a second order expansion, Taylor series expansion of f of theta, we can approximate this to be 1 over z e to the power minus f theta map. E to the power minus f of theta map, can you assume it to be some constant? Because f of theta map is a constant. So, e to the power minus f theta map is again a constant, z is a constant. Now, you have two constants, e to the power minus half theta minus theta map transpose the Hessian of f evaluated at theta map and theta minus theta map, right. Now, is it looking fairly similar to the multivariate normal that we have been seeing, right. Let us go back, we had this. Okay. Can you see the parallels between the two set of slides? PDF of some function of theta with a given mu and sigma covariance matrix capital sigma is some normalizing constant into e to the power minus half theta minus mu transpose covariance inverse theta minus mu, and what we have obtained on the right hand side is some normalizing constant into e to the power minus f theta map, which is again some normalization, some constants into e to the power minus half theta minus mu. So, mu turns out to be theta map, and our covariance inverse capital sigma inverse is the same as the Hessian evaluated at theta map, right, and then you have the theta minus theta map term. So, mu corresponds to theta map, covariance inverse corresponds to the Hessian of f evaluated at theta map, right. Once we know this term, which is the E term, once we know the E term and we know that the left hand side is a probability distribution. For probability distributions, we know that the integration has to turn out to be 1, right. We know the e to the power these terms. For normal distribution, do we know the normalization constant, right? We saw that it's in terms of pi and the covariance matrix, etc. All of those terms are well known, right. So, all we care about is we have been able to say that p of theta given d can be approximated as a normal distribution whose mean is theta map and whose inverse covariance is the Hessian evaluated at theta map, Hessian of the negative log joint evaluated at theta map. So, all that jugglery was only to be able to get something to this point, right. So, that is the essential formula. The posterior can be approximated to be a normal distribution with mean as theta map and covariance to be the Hessian of the negative log joint, the inverse of the Hessian evaluated at the negative log joint evaluated at theta map, right. Or I think the easier way to remember this is sigma inverse is the same as Hessian of f evaluated at theta map, right. And inverse here is there are way too many parentheses here, and we can also calculate the normalization constant if you want, right. But typically we do not need that, right. We just need to know that p of theta given d is some normal distribution, is a normal distribution. Questions on this? Okay. We will see some examples of this in action. Could you tell me can you tell me some situations where you think this would be very useful to use? The Laplace approximation, where might you find it to be useful to use? So, we want to compute the uncertainty in our outputs, but for doing that we need to have uncertainty in our parameters, or we need to compute the posterior. For Bayesian logistic regression like problems and for many problems, we cannot compute the posterior exactly, right, because the posterior involves intractable computations, integrals of things like Bernoulli times normal, right, which you can't compute. So, therefore, you have to approximate in some way, the posterior you have to approximate in some way. It seems to be a good approximation, simple approximation, because at least the mean is kept to be the map, which is intuitive. It is fairly quick to compute, largely it is a fairly quick thing to compute, right, because you have an analytical expression. But there are some downsides to it, that when the posterior is not unimodal, it will give you a very bad estimate. Can you draw a multimodal distribution? Multiple modalities means that it has got multiple humps, right, like a sine wave, right. Sine wave is an exaggeration, but it's multiple modalities. You're trying to get an approximation for that. It won't work well. It's also sometimes the inversion is computationally very unstable. You're trying to invert matrices, right. So, there are various approximations which have been done. Some of them are very cutting edge, and I link to this paper Laplace Redux, which implements the Laplace approximation for neural networks. Right. Now, let us take a simple example. First the unimodal case and then the multimodal case. So, the beta Bernoulli coin toss example. We know that the data has been given in forms of heads and tails. Our prior would be some beta distribution. So that will ensure that the support is only between 0 and 1. Our probability of heads is theta. Our likelihood for a single data point is theta to the power y1 minus theta to the power 1 minus y. Y would be either 0 or 1. We would get a figure like this. On the left hand side in the reddish magenta color, I am showing the prior, and on the right hand side I am showing the likelihood. The likelihood is highly bent towards theta equal to 1, close to theta equal to 1. It is centered at 0.9, right, because we have 9 heads and 1 tails. Where do you expect the posterior to lie, the posterior mode to lie? You have the prior mode at 0.5, you have the likelihood, the MLE at 0.9. So where might the mode of the posterior lie? Between 0.5 and 0.9, right? It lies between that. Maybe it's lying around this point, let's say 0.8 to something like that. This is just the map, right? Map means that the theta at which your log joint is maximized or negative log joint is minimized, right? So at this particular value of theta, we said that let's put a normal distribution with two things, the mean and the covariance, in this case just the variance, and it will turn out to be something like what we shown in the blue. So in the gray we know the true posterior. So we are showing this as an example because we know the true posterior for beta Bernoulli model. It's again a beta with alpha plus number of heads and beta plus number of tails, right? We know the true posterior, but we said that even if we didn't know the true posterior, we could have used a Laplace approximation or a Gaussian approximation centered at theta map, which is around 0.82, and with a known variance which we can calculate. Now we have already looked at a bunch of code. This is just going to show you that such calculations are not very difficult. Right, so first we need to define the negative log prior, which is just the beta distribution log prob at the theta. We can then define the negative log likelihood. So if you notice here that we have defined the negative log likelihood, we could have defined it in this way, dist dot Bernoulli prob is equal to theta dot log prob of data. We could have done that, or we could also do it in a simpler way for certain cases. When data equal to 1, then it's log theta, otherwise it's log of 1 minus theta. So we could have done it that way, and then it's just the sum over all the data points. Negative log joint is just negative log prior, negative log likelihood. We can optimize this using a standard gradient descent like procedure, and after doing this, let me run these. So we've been able to obtain theta map through this, which turns out to be 0.833. After that, we have drawn this same diagram. Now this is where we're computing. So you compute the Hessian over the negative log joint, right? Hessian function of over the Hessian of the negative log joint. You evaluate it at theta map, right? That becomes your inverse covariance, right? And because we're dealing with a 1D case, so we can get the posterior variance to be just 1 over the Hessian, over one of this Hess variable that we've computed, and we can then compute the scale to be posterior variance square root. So then this is the approximate posterior that we've got it. So normal distribution with mean to be theta map and the variance to be the the variance to be the Hessian inverse, where the Hessian is evaluated at Hessian of the negative log joint is evaluated at theta map. And this is where I'm mentioning the true posterior, alpha plus data dot sum. So alpha plus number of heads, beta plus number of tails. Okay, seems I didn't run this code. Right, and this is the approximation that we've obtained. Let's consider a multimode example. and we can try and get the normalized Laplace approximation for this, right. So first, could you think of how this distribution might look like? Can you draw that in your notebooks and see how it might look like? It's a combination of two Gaussians. It would be important to get the y also correctly, not exactly, but the relative scales. Okay, do you expect to see something like the following? You have two Gaussian distributions, you've added them up. Right. By the way, intuitions don't always work out so easily as they've worked in this example. You could try varying the means and the variances, and you may get totally different answers, and you may not be able to see that the mixture of Gaussians is existing. Here it's fairly easy to see. What do you expect the theta map to be? What would be theta map? So this is the, assume this is the function you're trying to optimize, right? What will be the optimum value? -2. How many think it's -2? How many think it's 2? The others are probably correct because it could be either, like depending on the way the gradient descent turns out, right? But if you do it with multiple restarts, the map would be -2. Right. If you are really unlucky, even with multiple restarts, you could just get stuck in this local maxima, and you'd pick up this to be the maxima. But assuming that you've picked up your optimization you've performed after multiple restarts, you'd obtain a Laplace approximation like this. Why is this bad? It has completely ignored all the mass at the second mode. Right. It's because it's going to center your distribution at this, it's going to center distribution at the mode that you've given it. So this is the Laplace approximation. As we discussed, going ahead in the next class, we'll be looking at Bayesian logistic regression, where we will have to apply a Laplace approximation in order to compute the posterior, because the posterior would require normalization constants, which are like integrations of Bernoulli times normal, which is intractable. So therefore, we'll put a Laplace approximation on that, get a posterior. Once you obtain a posterior, our objective is to obtain the predictive distribution, the P of y star given data comma x star. That will again turn out to be a huge problem, even though we have obtained the posterior to be a normal distribution, right? So we had the second integration, if you noticed. When we have to compute P of y star given x star, right, we had this integration. Again, this we could solve trivially just because both of these terms are normal. But again, for Laplace, for logistic regression, we'll say that the posterior we have said is approximated to be normal, but the likelihood is still Bernoulli. Right, and then you're again trying to solve this. So you will not be able to solve this trivially. Therefore, we'll study a topic known as Monte Carlo simulations. And Monte Carlo simulations will turn out to be a really powerful tool for various kinds of things going ahead. Okay, so this is where we'll end. Are there any questions? So given that it's the exam week, I'm trying to keep the topics a little light, but I don't think that turned out to be the case today. The next class should be hopefully lighter. Yes. I don't know. We'll have to think. So if you're talking, so what Utkarsh is asking is, he's bringing in some knowledge from variational approximation. Right? So there are other methods. So in this case, what we've said is that we are fitting in a normal distribution whose mean is specified. There are other methods which say that let's assume that the mean is also unknown to us, and let's choose one mean and one covariance which gets my approximate distribution to be as close as possible to my unnormalized posterior. Right. There are ways to solve that, which is known as the variational approximation methods. We will study them, and then it will become clear why Laplace is slightly different from variational approximation. Both of them are generally trying to fit normals to their normalized posterior. Okay, thank you.